Have you ever wondered how the electricity that powers our modern life gets to you and businesses around? It's a fascinating journey that starts at a power plant, sometimes hundreds of miles away, and ends at the outlet in our wall. But it's not a direct trip. Along the way, this electrical energy passes through several critical checkpoints. These places, often hidden behind fences with lots of wires and strange-looking equipment, are called substations. Every single light bulb that illuminates our homes, every hospital keeping patients safe, every factory building our cars, phones, airplanes, every data center storing our information, relies completely on the power that has been carefully managed and directed through these substations. Unfortunately, many people are not aware of this critical component of the power grid. Indeed, they are the silent heroes of our electrical grid, working quietly to keep our world running smoothly and safely. Substations play an incredibly important role in the reliable transmission and distribution of electricity. This is their core function. My name is Shaibu, a licensed professional engineer in the United States, a senior member of the Institute of Electrical and Electronics Engineers, and a senior electrical engineer with over a decade of experience in the power industry. In this video, I will simplify substation engineering for you to grasp the fundamentals. I am excited, and I believe you are as well. Now let's get into it. So, what is a substation? A substation is a specialized facility within the electrical power system. It serves as a central connection point for multiple power lines and assets. Its primary function is to manage the flow of electricity. It's not where electricity is made, like a power plant. Nor is it the final destination, like your house or office. Instead, it's an intermediary, a sorting and processing center for electrical energy. Imagine the power grid as a massive network of highways. A substation acts like a major highway interchange. A substation acts like a traffic control center. It directs electrical traffic. It changes electricity's characteristics and ensures safety. Electricity is generally produced at a lower voltage, which is not suitable for long-distance transmission due to electrical losses. As such, the voltage is converted to high voltage at the generator substation. Now the high voltage hits the highway, that is the transmission line, but that high voltage is too dangerous for local streets or your driveway. To understand better, here are 4 key functions. First, changing voltage levels. Transformers, massive devices. Step up voltage for long-distance transmission. Step down voltage for local distribution. Second, routing power flows. Switches and circuit breakers open and close pathways. They redirect power or isolate sections for repairs, like a train dispatcher. Third, protecting the grid. Faults caused by a lightning strike. Faults like a tree falling on a power line. Protective systems detect faults in a fraction of a second. Circuit breakers automatically isolate damaged parts. That prevents small problems from turning into wide blackouts. Fourth, monitoring and control. Sensors measure voltage, current, and power flow. This data is sent to a central control room for remote management. Not all substations are the same. Transmission substations. These operate at the highest voltage levels, typically 115 kilovolts and above. They connect transmission lines and often support regional power flow. Distribution substations. These step voltage down to medium voltage levels and supply cities, towns, and industrial areas. Switching substations. These don't change voltage. Their job is reliability. Switching lines in and out during maintenance or faults. Collector substations. They collect power from generating stations like solar plants, wind farms, or battery storage systems, and connect them to the grid. They are essential for integrating energy sources into our existing power system, acting as the on-ramp that allows power produced to merge onto the electrical highway. How do engineers design and understand the complex web of connections inside a substation? They use a single-line diagram, or SLD, a simplified schematic representing a 3-phase system with one line. It's the master blueprint for a substation, It shows major equipment, transformers, circuit breakers, and switches, and how they connect. The SLD makes power flow paths clear at a glance. It shows how sections are protected and where measurements are taken. Learning to read an SLD is one of the most important skills for any power engineer. Beyond the SLD, the physical layout on the ground is critical. Common substation configurations balance cost, reliability, and operational flexibility. Firstly, single bus. This is inexpensive but less reliable. A problem on the main bus can shut down the entire station. Secondly, main and transfer bus adds a backup bus to allow maintenance without a full outage. Thirdly, we have the ring bus. 2 paths to every circuit, so operation continues even if one breaker is out of service. Moreover, the breaker and a half scheme. This has 3 breakers for 2 circuits, highly reliable and flexible for critical high-voltage stations. Choosing the right layout involves careful trade-offs between reliability needs and budget. The most prominent and often most expensive piece of equipment is the power transformer. This is the heart of the substation. It changes voltage levels. Transformers are massive, oil-filled devices that can weigh hundreds of tons. They work on magnetic induction. They step voltage up for transmission or step it down for distribution. Size and capacity are rated in megavolt amperes. Because they are huge, costly, and have long lead times, protecting transformers is a top design priority. To protect transformers in the grid, substations use circuit breakers. Circuit breakers are the ultimate safety switches. They interrupt the flow of electricity, especially during faults when currents can be several times the nominal circuit current. Modern breakers often use vacuum or an insulating gas like sulfur hexafluoride to extinguish the arc when contacts separate. That stops the immense fault current safely. Working alongside breakers are disconnect switches. A breaker interrupts large currents. A disconnect switch does not, unless it is designed to load break. Disconnects provide a clear, visible air gap, ensuring equipment is fully de-energized and isolated. Opening one underload would cause a dangerous, uncontrolled arc. Verify if your disconnect switch is designed to operate under load conditions, else be cautious and follow the best operating procedures. Instrument transformers, current transformers, CTs, and voltage transformers, VTs, are the senses of the substation, scaling high currents and voltages to safe signals. For instance, CTs can step down high primary currents, say 4,000 amperes, to secondary currents of 1 or 5 amperes. Those small, accurate signals feed the brains, relays, meters, and communication equipment that monitor the grid and operate breakers during a fault. In a place filled with such immense electrical power, safety is the absolute highest priority. One of the most critical safety systems in any substation is its grounding system, a network of buried copper conductors. It connects metallic structures, equipment frames, and fences. During a fault, large currents flow into the ground. A properly designed grounding system safely dissipates this current. This protects against touch voltage and step voltage. A well-designed grid keeps these voltages below lethal levels, creating an equipotential zone. Crushed rock adds surface resistance and further increases safety. Soil resistivity is the most important input to ground grid design. Different soils vary widely and impact the design. Engineers also consider maximum fault current magnitude. Standards like IEE Standard 80 provide detailed design and testing guidance. Beyond grounding, secure fencing, clear warning signs, PPE, and rigorous lockout-tagout procedures. Every rule and every piece of equipment is there for one fundamental reason: to protect human life. This is the job of the protection and control system, the brain and nervous system of the substation. Protection systems exist to do 3 things: detect faults, isolate faulty equipment, maintain system stability. Key principles include selectivity, speed, reliability, dependability, security, stability. Selectivity trips only the breaker closest to the fault, keeping the rest in service. Speed matters. Relays operate in milliseconds to limit damage. Reliability means dependable operation and security against false trips. Overcurrent protection works like your home breaker. If current exceeds a set limit for a time, it trips. Differential protection compares current in and out. A mismatch signals an internal fault and trips immediately. Distance protection calculates impedance to estimate fault distance and decides within zone boundaries. Bus protection must operate with extreme speed for one of the most severe events in a substation. Traditional substations carry current and voltage signals and control commands over thousands of copper wires. Digital substations convert analog to digital at the yard and use fiber or other efficient communication means. IEC 61850 defines a common language for intelligent electronic devices so multi-vendor gear can interoperate. This simplifies design, commissioning, and future upgrades. Digital substations provide richer data for better remote monitoring and faster fault analysis. Automation can reconfigure the grid to restore power, reducing outage times. With renewables, substations integrate battery energy storage, charging when generation is high and discharging when demand is high, smoothing fluctuations and improving reliability. Substation engineering offers stability, intellectual challenge, and the satisfaction of performing a vital public service. Career paths include design engineering, protection and control, field commissioning, and asset management. Key skills: strong fundamentals, understanding of standards, practical field awareness, and growing digital skills. Know essential standards of the Institute of Electrical and Electronics Engineers, the National Electrical Code, and the National Electrical Safety Code. Build skills in network communications, cybersecurity, and modern IED software. Most valuable, practical field experience. Visit substations, talk with experienced engineers or technicians, and learn from mentors. Substations are where physics, engineering, protection, safety, and reliability come together. If you truly want to understand the power grid, start with substations. If you found this video useful, like the video, subscribe to ShaiLearning, and check the links below for detailed articles, tools, and learning resources. I'll see you in the next one. Have a good time.